A fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth on December 17th. Comet, asteroid, or something else?
In the long hunt for other minds, we expected a voice and instead found a visitor. It appeared as a faint streak in a crowded star field, then as a curve of light that refused to behave. Numbers turned odd. Expected chemistry arrived lopsided. Motion that should have drifted stayed steady. If this object is natural, it asks for new physics for familiar ice and dust. If not, it may be the first artifact we have tracked across our sky. Either way, our method is shifting from listening for calls to studying what passes by. Artifacts, not signals. For decades, classic SETI assumed civilizations would broadcast. We aimed radio dishes and lasers at the sky and searched for patterns, one pulse, one beacon, one coded invitation. In the silence, another path appeared. Sometimes a solid body crosses the gulf between stars and enters our solar system. If technosignatures exist, one could look like this: an object, not a transmission. Modern astronomy has confirmed only 3 interstellar visitors: 1I Oumuamua, 2017, 2I Borisov, 2019, and now 3I/a TLAS. Among hundreds of billions of comets bound to our sun, only a few came from elsewhere. Each is a rare chance to catch something built, not born. Artifacts outlast their makers and can preserve technology and intent. Unlike a fleeting signal, a relic endures photographable, measurable, perhaps interceptable. Oumuamua expanded the playbook. The hunt for technosignatures now includes what passes by, not only what we hear. In that light, 3I/Atlas is more than another comet. It is evidence in transit. 3I/a TLAS drew attention because expectation failed against observation. Its brightening should have followed simple geometry, yet in 4 weeks, its light rose 5-fold beyond predictions. Spectrographs found metal lines where they should be scarce, and despite a visible coma and tail, the path barely veered. If 3I/Atlas is natural, each contradiction needs an explanation. If not, we may have watched an interstellar visitor under control. The first detection was quiet. On May 7, 2025, NASA's TESS recorded a faint fast mover near the galactic center. No alert fired, the signal hid in stellar clutter, and its motion was too subtle for triggers. Night after night, it slipped into full-frame images as a ghostly trace. On July 1st, the Atlas survey in Chile flagged an anomaly. Since TESS first caught it, the object had brightened about 5-fold while still hugging the Milky Way's bulge. The Minor Planet Center logged the alert, and observatories pivoted within a day. Teams searched archives. ZTF and Pan-STARRS found pre-discovery images from late June with a steady trail. Amateurs filled gaps from mid-June onward. The light curve emerged, a smooth rise geometry alone could not explain, partly hidden by crowding in Sagittarius. Only after the alert did its early activity become clear in terabytes of frames. Between May 7 and June 3, 31, Atlas brightened by 5 times while moving from 6.36 to 5.46. AU standard geometry predicts 1.5 times, not 5 times. Photometry from TESS, ZTF, and Atlas agreed, cross-checked against field stars with systematics under 1/10 of a magnitude. This was not a brief outburst or instrument quirk. The coma was visible far beyond the water ice line, and the dust cross-section grew from 300 to 1,700 square kilometers by July. Error bars were small. Background confusion could not explain the excess. Prosaic causes calibration issues. crowding artifacts. Lucky alignments failed. The curve was consistent across instruments and continents and too early for water-driven activity. Some proposed underestimated closing speed in the dense field. After recalibration, the extra flux remained. That left bolder ideas. Engineered braking far from the sun could cause sustained brightening without water sublimation. But extraordinary claims need extraordinary evidence. Caution held until the chemistry added its own puzzle. VLT spectra detected nickel in the coma-clean lines above background, while iron was missing. In most solar and cometary material, iron and nickel appear together. The Sun's photosphere has approximately 18 iron atoms per nickel. Even dust-rich comets rarely show nickel exceeding iron by more than approximately 2 times. IN3 I/ATLAS Ni/Fe appears greater than 15, perhaps greater than 50, with iron undetected. The team led by Dr. Sophia Cardenas mapped transitions and estimated a nickel production rate near 4.6 grams per second at approximately 2.85 AU. Strong upper limits on iron pushed the ratio off the charts. Natural ideas struggle. Nickel carbonyl can vaporize at low temperatures, boosting nickel relative to iron, but iron carbonyl is far less likely. Selective sputtering or unusual fractionation might help. Engineered residue from nickel-rich. Superalloys is a more provocative option. No clear propellant or alloy fingerprint has appeared, only nickel standing alone. The ledger is unbalanced. The natural mechanism remains unclear. Trajectory. Data deepened the paradox. From July through August, the orbit showed only approximately 1 to 1.5 kilometers per day of non-gravitational drift, even as a large coma and tails were visible. Solar system comets act like rockets. Vapor jets push the nucleus off course. Here, the path looked nearly gravitational, as if the body were inert stone rather than venting gas and dust. The rocket effect seemed suppressed. Comparisons sharpen it. 2 I/BORISOV, a classic active comet, drifted approximately 100 kilometers per day from outgassing. By contrast, 1 I/Oumuamua showed large acceleration without detectable gas or dust. Now 3 I/Atlas presents the inverse of oumuamua, a clear coma with only 1 to 1.5 kilometers per day, drift about 100 times less than Borisov, and a small fraction of oumuamua's. 3 objects, 3 mismatches. How could 3 I/Atlas vent visibly and still hold its course? An extremely massive nucleus would mute thrust, but photometry constrains size. That leaves control. Stabilization or geometry that cancels thrust. No known natural process fully bridges the gap. As data improved, the drift stayed near a kilometer per day, far below expectations for an active comet. The contradiction is mechanical as well as mathematical. The Atlas anomalies. Brightness, from May 7 to early June, 3 I/Atlas. Brightened 5-fold far beyond the water ice line. TESS, ZTF, and Atlas agree. The coma appeared early. Dust cross-section grew from approximately 300 to greater than 1,700 square kilometers by July. Either exotic low-temperature volatiles drove activity, or another energy source was at work. Chemistry. Strong nickel lines with iron undetected imply NIFE greater than 15, perhaps greater than 50, with Warbart 4.6 gigas per second, of nickel near 2.85 astronomical units. Natural explanations exist only at the margins. An engineered source cannot yet be ruled out. Dynamics. Almost no non-gravitational acceleration, despite visible outgassing. Compared with Borisov's approximately 100 kilometers per day and Oumuamua's large drift without a coma, 3I/ATLAS shows the inverse pattern, suppressing the rocket effect. This strongly requires implausible mass or control cancellation by geometry. No single natural model fits all three anomalies at once. Skepticism remains essential. The sky has fooled us before. Yet the pattern is hard to ignore. Timing that hints at controlled deceleration, chemistry that breaks the iron-nickel partnership, and mechanics that mute outgassing forces. If 3I/Atlas is natural, it is unlike known comets. If artificial, its behavior fits a controlled visitor easing into the solar system. What comes next? The Vera C. Rubin Observatory and its legacy. Survey of space and time will sweep the southern sky every few nights, making the next interstellar visitor hard to miss even in crowded fields. Real-time alerts will give the community a running start. But large telescopes cannot do everything. When 3I/Atlas brightened against the galactic bulge, amateurs stitched together the early light curve from public data. A global network, Rubin, Pan-STARRS, Atlas, and backyard stations now functions like a single instrument, shrinking error bars and sharpening models. As Atlas rounds the sun, every night counts. Coordinated campaigns track the light curve and spectrum. Early warnings ripple through forums, triggering follow-ups from telescopes large and small. In this new city, discovery is not reserved for professionals. The best clues may arrive not as signals, but as objects whose motion, chemistry, and light refuse the rules. The latest measurements capture three tensions in one body. Spectroscopy shows nickel without iron, an unusual signature that challenges standard comet chemistry. Astrometry shows almost no non-gravitational acceleration, despite visible outgassing, dynamics at odds with textbook rocket effects. And history reminds us that our two previous interstellar visitors broke molds in opposite ways. Borisov behaved like a classic comet, while Oumuamua deviated strongly without a coma. These opposing anomalies remain unexplained. No evidence yet confirms artificial control. But 3I/Atlas exposes seams in our assumptions, forcing us to test every natural mechanism and, if they fail, to consider intent. Each interstellar visitor is a singular opportunity, a probe from a time and place we may never see again. Whether 3I/Atlas is natural or engineered, the message is the same. Expand the search, widen the methods, and be ready. Proof may not arrive as a voice in the dark, but as an object moving through our sky, carrying answers in how it shines, in the atoms it releases, and in the path it refuses to leave.